Hello and welcome to chemical bonding. So to bond or not to bond, that is the question. There are two main reasons that an atom would bond. Those two reasons have to do with stability generally and how stability is kind of acquired or how it's obtained. So one reason that an atom would bond is to get a full valence shell. We call that, remember, a stable octet. Another reason an atom would bond would be there's a mutual attraction there. For electrons, like two nuclei. And overall, the combination of, this full valence shell idea, the stability, the attraction idea kind of leads to basically stability. So to break this down just a little bit more for you, a full valence shell means getting 8 valence electrons for most atoms, except the really small ones that only want 2. So one thing that we've talked a little bit about already is the idea of ionic bonding. So if you move this guy over here, so sodium's losing an electron to chlorine, we get these new ionic configurations, 2,8 and 2,8,8. These configurations are very stable. Both of these atoms now have a noble gas configuration or a stable octet. So since they feel like they have that configuration, they're happy, they're stable, and they're, bonded, and they're going to probably stay that way unless we mess with them. We also have that simultaneous attraction for electrons by 2 different nuclei. Nuclei have a positive charge because of protons, and electrons are negatively charged. So what you see in the little diagram in front of you is these 2 electrons right here could be shared, or maybe they're getting transferred or something like that, but they're both experiencing a pull toward 2 different nuclei because of the opposite charges attract idea. So just like people like to form friendships with each other and relationships just to really complete their lives, atoms are doing the same thing to complete their valence shells. And there are some energetics involved with this that you need to know some of the basics of. Bonding changes potential energy or chemical energy. So if we actually made a little energy diagram showing potential energy on our y-axis, whenever a bond breaks, so if we're talking about this bond right here, just between a couple of random, hydrogen and oxygen, if we were to actually break that bond, when these guys are separate, they actually have more potential energy. They actually have, they actually are a little bit less stable now. So what actually happens during bond breaking is we actually put energy in, and by putting that energy in, so that requires energy, which just makes this an endothermic or energy absorbing process. We then separate these guys. They're in this really high energy kind of unhappy state. And in that really high energy unhappy state, they're kind of just roaming around being a little bit crazy. They're actually considered to be pretty unstable. So when we break a bond, we make things more unstable. So we have a decrease in stability. Whereas if 2 single atoms floating around out there in the world find one another and they bond, that makes them very happy. Because once they've bonded, they actually are able to sort of give some of that excess energy away. They're very happy, they're more stable. So this is showing over here an increase in stability. And when bonds form, energy is actually released. So when we think about things like, burning a fuel or something like that, what's actually giving up the energy is the formation of new bonds in that process. So forming a bond releases energy. That energy goes to the surroundings. So bond formation is an exothermic process. And keep in mind overall, lower energy is going to give you higher stability. Things that are high energy, kind of like a very hyperactive, crazy person who's unpredictable, doesn't make you feel very stable when you're around that. We do have a couple of mnemonic devices that we like to use for this. So one that's pretty commonly used by a lot of different chem teachers I know is BARF, which is break, absorb, release, form. When you break a bond, you put energy in. So breaking a bond requires energy is absorbed. When a bond is broken, you release energy. Or I'm sorry, when a bond is formed, you release energy. So release form. That energy is given away to the surroundings. Got to sign this one for Mr. Irby. This is his own creation. Break in, make out. You want to break a bond, you put energy in. You want to make a bond, energy comes out. Really popular with the kids, that one. One thing we will need to do is a quick review of Lewis dot structures. These are just Lewis dot structures right now for atoms. We also need to do a quick review of them for ions as well. So for atoms, you're simply doing just the valence electrons that are present. So a little definitional review. Valence electrons are your outside or bonding electrons that we do show in a dot diagram. The inner kernel electrons are non-bonding electrons. We do show these when we make Bohr diagrams. We do not show these when we make Lewis dot structures. Those only are bonding valence electrons. Just a little review if you're looking at sodium. Sodium has 1 valence electron and a total of 10 kernel electrons. Just a little review of those two terms. So take a moment, grab your periodic table, pause the video, and fill in your dot structures for these, and we'll go over them in just a moment. Main rule to keep in mind is no more than any 2 electrons on any one side. Something that is going to come up, and I apologize, I really don't have this in your packet, but just to do a quick review of making ionic dot structures, I'm just going to pull this up on a separate slide. Just make sure you kind of remember this general process. If we have an atom of magnesium, it has 2 valence electrons. So it has that configuration 2A2. We're showing those 2 bonding electrons right there. If we wanted to show the ion for this, the ionic dot structure for this, we're actually going to lose these 2 electrons. But that's still the same ring we want to show. Those are our bonding electrons, and we do want to show people that they went away. So we're going to show magnesium with no dots, but when those 2 electrons were lost, we got a positive 2 charge. Some people like to throw brackets around these. That's cool. Our other one that we'll look at a nonmetal for a moment. We'll take a look at oxygen, which typically has 6 valence electrons when it's in its regular old atomic state. So our valence shell is this shell right here that currently has 6. Oxygen is very close to having 8, so it's going to gain 2 electrons. So our oxygen dot structure will actually show all 8 of those electrons, since we're becoming 2-8 and we're showing that second PEL. But we do need to tell people that we've got that negative 2 charge. And again, you can throw brackets around this if it makes you feel better. That's about it for our introduction to bonding. We'll go on to ionic and covalent bonding next.